And here we confront an unexpected and in many ways unwelcome limitation on our ability to understand all kinds of things about the world around us, from the economy to society to climate, using the standard scientific method of quantification, of measurement, of attaching numbers to things, and then of using mathematics to analyze and predict, including increasingly through computers. As Wikipedia again put it, the causes of ice ages are not fully understood for either the large-scale ice age periods or the smaller ebb and flow of glacial interglacial periods within an ice age. I like not fully understood. Try to put this into an equation. You can't do it, and that is where this whole notion of modeling really falls apart. Modeling depends upon the idea that even complex phenomena like climate are essentially susceptible to the techniques of linear algebra, that we can identify a few key inputs, we can figure out a few functions that explain how these inputs relate to one another and to other factors, and then by solving these equations using our mighty computers, we can predict the outputs. But we can't. Even the IPCC itself in 2001 said, in climate research and modeling, we should recognize that we are dealing with a coupled nonlinear chaotic system, and therefore that the long-term prediction of future climate states is not possible. And here you're going to run into one of the major problems with the whole enterprise of modeling, and that is chaos theory. Yes, folks, it's a math lecture, but don't worry, we won't do any actual math, and we'll get pictures a lot prettier than some of those charts. Maybe some of you remember chaos theory. It was very trendy back in the 1980s and 1990s when James Gleick's coffee table book Chaos appeared in 1987. And it was driven by the discovery of the so-called butterfly effect. I actually got a mailer from The Economist at one point saying I should subscribe because I'm the sort of smart, sophisticated guy who reads our publication. And in order to burnish this self-image on my part, they quoted, "When a butterfly flutters its wings in one part of the world, it can eventually cause a hurricane in another." In a great many cases, we can't model things mathematically because the outcome of what look like fairly simple processes turn out to be, quote, sensitively dependent on initial conditions. And the critical paradigm for unpredictability is weather and climate. This was discovered, in fact, through an effort at computer modeling. Konrad Lorenz was attempting to simulate climate. Now, it was on a very primitive computer. You may know the lunar module that landed man on the moon in 1969 had 64K of memory. That's right, 64K. Lorenz was working in 1961. He'd have been lucky to have 64. But he was simulating weather, and he'd run a series, and then he wanted to see what would happen next, and he didn't want to have to wait for the whole thing to run. So he just took the printout, took the data from near the end, and punched it in and ran it. But to his amazement, even before it got to the end of the simulation he'd already run, it diverged dramatically. And his first thought was, my computer's busted or something. These are simple linear equations. This shouldn't be happening. And then he thought, hang on. The computer was actually calculating to 6 decimal places, but it only did printouts to 3, so I fed in 3, not 6 decimal places. And in a way that explains the divergence, but in a way it doesn't, because I fed in the 3 most important decimal places. And the whole idea of using linear algebra to solve scientific problems, which has been enormously fruitful over the last 500 years in fields like physics and chemistry. Virtually all the technology you see around you is a product of its effectiveness. But nevertheless, it relies on approximations of inputs. And he had put in approximate inputs, and as Essex and McKittrick put it in Taken by Storm, a mathematician's toy model of atmospheric turbulence revealed a remarkable thing. Small things had big consequences after all. And it's hard to overstate the impact of this. It's as though you discovered that in trying to create fair boxing matches, what mattered was not the kilograms, but the grams. And the trouble with that is that it makes all kinds of modeling and prediction impossible because you can never know with enough precision what all the initial conditions are. Now, this picture I'm showing you is a graph of a simple child's toy. It has a piece of metal on a string, and there are 3 magnets at the bottom. And you start it somewhere, and it swings around, and the magnets pull on it, and it orbits and orbits, and finally it stops, and it must stop pointing at one of the 3 magnets. But which one? If a point is green, it means you start it here, it will end up on the green magnet. If it's blue, it's going to end up on the blue magnet. If it's red, it's going to end up on the red one. And obviously, if you start very close to one of the magnets, it has a strong tendency to wind up right where it started. But the further out you move it, you notice that the pattern isn't just divided, as you might expect, into 3 pie-shaped wedges. It's incredibly ornate and elaborate. You say, okay, well, that's fine, so it's ornate. All we need to zoom in, and we will find the point and know where it's going to end up, right? But the problem is, if you zoom in, this fractal pattern that you're seeing just keeps blossoming at you. You dive down and you keep getting these mysterious, beautiful, but puzzling patterns of red, blue, and green. And that means we cannot feed known but slightly approximate data into a computer and predict the outcome of the magnet's path, because we can never know it to enough decimal places and it matters.